MOXIE experiment that extracted oxygen from CO2, compressed it, and got it out. And then obviously we need the power. We need a lot of power. It could be solar power and the nuclear power. Probably it's going to be hybrid system, both the nuclear and the solar. And all of this goes into a production plant. So we need water electrolysis and Sabatier reaction to get the oxygen and methane out to make our dream possibility. So what is red water? Well, red water consists of, it's primarily this thing that you see rotating on the right-hand side. It's a drilling and water extraction system, and it's placed on some kind of a mobility system. In this case, what you see is an athlete rover. Athlete rover also has water storage tanks, compressed gas, and obviously mobility. The red water itself has called tubing. It's a big drum to drill below the ground. It has an injector to actually push the cold tubing into the ground, and so-called bottom hole assembly with an inflatable packer and the melting system to extract water. All right, so how did we arrive with this system? We actually, the cold tubing has been around for decades now. It's used in oil and gas industry to drill thousands of meters below the ground. It's a 3-4 inch diameter tube that could be steel tube that comes out of a gigantic drum and goes through a so-called gooseneck on the right-hand side, and therefore injector, and goes down below the ground where it does all the drilling. So our job was to scale it down and make it super light in order to be put on Mars. So this is a red water system with steel tubing with the injector. But the very first implementation of this cold tubing in planetary setting is going to be on the moon. We are flying at the end of the year on a Blue Firefly Aerospace Blue Ghost lander to Mare Crisium. It has an instrument called LISTER, which is a heat flow probe, to pneumatically drill 3 meters below the ground. And what you see on the right-hand side is the 1/4 inch steel tubing that goes through the injector right over here, and they inject gas, and by injecting gas, it blows literally regolith out of the hole. And it's not just fine regolith. You're talking about rocklets, approximately 1/4 inch rocklets that are being literally blown out of the hole. So this is a 1/4 inch on the right hand side, whereas red water system is a 1 inch tubing, significantly stiffer because we obviously have to drill through cryogenic ice and rocks to get down, tens of meters below the surface. In terms of water extraction, again, this technology has been to some extent used in Antarctica in the South Pole. The idea is to drill a hole into ice, put a water pump, and then initially inject hot water. Hot water would melt some of the ice to make cold water, and then the pump would pump cold water into the heat exchanger, and they would pump hot water back into this ice cavity to melt more of the ice. And some of the cold water pumping out would be filtered out and cleaned, and taken and used in the South Pole of Antarctica. So this technology has been used literally for decades. It has also been demonstrated in Greenland back in the 60s. It works. The only obviously difference is here we're using a pump we have significant atmospheric pressure, whereas on Mars we have very low atmospheric pressure and very difficult to use pump because we're so close to the triple point of water and can get cavitation. So we've done initial testing to see whether actually we can drill and melt, and voila, we actually could do it in the lab. In terms of a concept of operations, to do all of the stuff that I just told you, we essentially following 4 steps. The first one is pneumatic drilling. So we lowering the cold tubing down, we drilling, and we inject compressed gas to blow the cuttings out of the hole. Once at depth and once in ice, we are inflating the packer right over here, pressurizing the borehole. Then we start rotating a drill bit and start heating a drill bit to melt water. And finally, we repressurizing the borehole. So this is high pressure over here, low pressure over there. We open a valve and water under pressure flows through the tubing into the tank. This is step 1, which is a pneumatic drilling. So we took a breadboard of cold tubing. We had a stash of ice blocks, and we have a injector system. You can see ice being blown out of the hole during drilling. We could do something like 2 meters an hour in ice with just shy of 200 watts of electrical power and 300 newtons weight on bed. So that's the force required to drill. And you can see a stash of ice blocks with a bottom hole assembly and the injector system right on top. So that's step 1, pneumatic drilling. Step 2 is inflation of a packer. So this is a breadboard, again, in a lab. It obviously has to be flexible to inflate it. And we're using the same gas pressure that we're using for blowing cuttings out of the hole. So this is done, left picture shows on the left-hand side in some kind of a tube. Picture on the right-hand side, it's done in ice at cryogenic temperatures to show that actually our material can withstand these low temperatures. And we pressurize the borehole to also show that we can retain the pressure at these temperatures and the sealing conditions. So the borehole sealing and worked pretty well in this case. Then the final step, or one of the final steps, is melting. Here we started to rotating drill bit. We actually put a die. So we put a die through the pneumatic tubing to show you how this rod well is being formed. The ice temperature is approximately -10 degrees centigrade. This is our freezer, walking freezer in Altadena, outside of just across the street from NASA JPL. So one of the coldest places is in LA, is in our walking freezer, and it worked. Here, obviously, it's a sped up melting process, but the critical part of this is that drill bit kind of rotates, sort of like when you try to dissolve sugar in a hot tea, right? You rotating, using a spoon to rotate it. Same thing here, using a drill bit to actually do the rotation and stirring up, do some convective heat transfer, and that's how you can melt. So let's go to the final step here. This is a picture inside the vacuum chamber. We are so this water and this a container is sealed. Water tank is exposed to Mars atmospheric pressure. So this vacuum chamber is at Martian pressure. So what we did here, I'll show you again. We pressurized this container, so that's, imagine it's a borehole, and then water under pressure flows into the container. And on the right-hand side, we did the same thing in ice. And the moment you pressurize it, we open the valve, and voila, we get water. Again, it was dyed on purpose into a container. So all these 4 steps done crudely in a lab work, which gave us confidence that this system actually could potentially work on Mars. So our next step is to design a TRL-5 system. So here, when developing first brass board. We didn't worry about the power. We didn't worry about the volume. We didn't worry about the mass of the entire system. Idea was to essentially show end-to-end all the 4 steps in the vacuum chamber and in our freezer. So this is final system as drawn. The drum diameter is just shy of a half a meter. It's mainly driven by the size of our vacuum chamber. So you have cold tubing going through the injector. These are this bunch of drive rollers and pinch rollers that whose job is to turn this 1-inch diameter metal pipe into a straight tubing. Down below, you have a so-called bottom hole assembly. And if you were to have X-ray eyes, you will see it's not just hollow tubing, but it's a bunch of motors, bunch of heaters, actuators, tubing, all in order to drill, to blow the cuttings out of the hole and to melt them. This is our electronics set up outside of the chamber. This is wall of the chamber with cables going in. These are the design parameters, and these are the test data. So we actually, our test data is actually pretty good. But what it shows that our initial design was pretty much spot on in terms of what we're expecting to see. We have over-designed our heaters. We have over-designed our drilling. But so far, all the test data worked extremely well. So initial tests were done in our walk-in freezer. It's a 5-meter tall freezer with a scaffolding, bunch of cameras all over the place. The drum with the cold tubing sits right over here on top of blocks of ice. And this is actual picture. Just to give you an idea that it's relatively big system. The cold tubing is end-to-end is just over 2.5 meters tall, and then you have stash of ice blocks also close to 2 meters tall. And then we have a bunch of ice blocks that we had to fuse together to form sort of one single fused ice fixture. And we drilled down. And then finally, we pressurized the borehole. We set up a packer, and you've seen this video before. But the final volume was approximately 12 liters. The heater on a drill bit was around 46 degrees centigrade. We needed approximately just over 1 kilowatt of power. The wall temperature, so this water that you see, dyed water, is around 8 degrees. Ice temperature was around -6 degrees. The energy that we put in was 2 kilowatt hours. So our melting efficiency was 50%. So 50% went straight into the melting, and 50% was lost through ice, because we were essentially warming ice blocks from like -10, -15 centigrade to -6 degrees centigrade. So it's still not bad in terms of energy required to melt. And picture on the right hand side shows you this entire system with the cold tubing and the drum right on top. And then we put entire system into our 3.5 meter Mars chamber. So it's the shroud on the outside. We have a drum with liquid nitrogen lines to freeze ice. This is our cold tubing with the injector, with the bottom hole assembly. You can see the shrouds on the outside to pre-cool the entire surface, entire volume of air inside it. It's meter by meter, so this thing is just over half a meter in diameter and meter and a quarter tall. So we drill down under Mars conditions, and then we melted water and we put dye, and this is the shape of our red well frozen in place. We essentially took a chainsaw and we cut this drum in half to essentially see how this entire column, work, and if we had any fractures and how much water we melted. But before everything was back frozen in place, we pumped some of the water. Um, this jar was actually inside the inside TVAC, so we pumped some of the water into the container to show that actually we can do this kind of stuff. So overall, almost 7 liters. The heated power was just shy of kilowatt. Well, temperature was 9. So this red water down here was close to 9 degrees centigrade. Ice temperature was -70. So that's the ice temperature that we expect on Mars. Heater was around 2 kilowatts, and melting efficiency was approximately 30%. Lower efficiency because obviously we have much colder ice. But it's very difficult to have something that has 100% efficiency. I consider 30% in these sort of conditions to be actually very, very good. So what's next? Well, then we took all the lessons learned and we designed our TRL-6 system. So we made sure that the system is actually light in mass, cold tubing. The metal is, obviously the processes to do it more refined. Bottom hole assembly right over here is better packaged. The injector is smaller, 2 as opposed to 6 of these rollers. So overall, this is our final TRL-6 system. Just over 2 meters tall, almost half a meter by half a meter, close to 100 kilograms in mass. And these are the main components. So you can see the cold tubing, injector system with actuator. The cold tubing itself is not just hollow, it's got a bunch of copper wires and power and the data down. It's got hollow tubing for gas and pumping water to the surface. And the bottom hole assembly has 4 main subsystems: heated drill bit, some slip rings with motor assemblies, fluid transfer, and the packer assembly. So we did TRL-6 testing. We went back to our vacuum chamber, to our freezer. So this is scaffolding. We lifted entire system out. Above the on top of the scaffolding, we put ice, and this was a final system. And we showed initial pneumatic drilling at just over a meter an hour. You can see the snow essentially ice cuttings being blown out of the hole. Here we start also heating a little bit to show that you can start melting while you're drilling. These bubbles is because we are actually pumping gas through this. Here we doing a Rodwell formation. You can see formation, this beautiful conical shape formation of a Rodwell, approximately 2 liters with 300 watts electrical. And then we did inflating of a packer in ice, and finally melting and pumping water. You can see water is being pumped into this container. So all those 4 systems worked really well. The next slide. So it was great success. These are the 2 containers we filled, and this is a beautiful picture of our Rodwell in this crystal clear ice. So what's next? Well, this thing is not the Rodwell can not necessarily be used just for drilling and melting. It could also be used for astrobiology missions to drill tens of meters into the ground. We can put downhole instruments. So this is a microscopic imager, near infrared spectrometer, neutron spectrometer, dielectric permeability probe, temperature sensor, heaters, and so on. All of this stuff can be packaged inside the drill. So as you're drilling down, you can actually do the sensing. You can capture cuttings and put them into the mass spectrometry instruments. This would be our drilling platform, which could be delivered by Skycrane to the northern polar regions of Mars, just Phoenix, just like Phoenix did. And at this point, I think most of the technology is well understood. Skycrane, we know how to do that. The landers without, there's no propulsion system, so it's not really a true lander. It's a drilling platform. Power, whether it's RHUs, MMRPGs, or solar. Redwater is at TRL-6. By the way, the Redwater for astrobiology mission is called IMPACT, investigating Mars geopenetration and analysis with cold tubing. Compressed gas, MOXIE has shown it, and then we have a lot of different instruments for light detection that you can also use. The same system obviously can be also used on the surface of the moon to drill tens of meters below the ground. It's I wouldn't really change much. The bottom hole assembly could be exactly the same. Injector and drums, gas tank, all of the stuff could be exactly the same. The difference between Mars and the moon is that on Mars, you need to consider contamination control and clean your system before you start drilling because of planetary protection. On the moon, you don't have this requirement. But otherwise, the two systems would be pretty much identical. During the process of a couple of years development, we've done a outreach with the students, and Redwater was also featured during Rascal competitions, and the teams that featured Redwater actually won the best paper awards. So this is a testament to the technology, and that even students are very, very interested in future Mars exploration and the water mining and this sort of thing. So the good news is that we're going to have plenty of students out there that are going to try to get into the space industry and make this reality. Lots of publications. If you are interested in all of this, a lot of details have been published. It's been featured online and in a New Space magazine. You can see the cover for this journal. And with this, I'd like to open to questions. Thank you. Maybe you can type the questions if there is obviously time. And James, you also I'm going to put myself on mute and then give me thumbs up to respond. I can't exactly remember the exact mass, but it's a thin wall. We use thin wall aluminum tubing at the end, and remember, it's not just tubing; it's all the copper wires inside it. So I can't remember on the top of my head, but I can give you information. But yeah, in terms of depth, no. That it's much, because it's a solid tubing, right? It's well protected from dust. All the competing technologies is individual drill strings that have to be coupled to each other, and this requires bunch of feed-throughs and there's some kind of dust-tolerant connectors, robotic systems on surface to deal with all of this. And you still need gas because the auger could only work maybe first couple of meters, and then you still need gas to blow the cuttings out of the hole. So we looked at the robotic system like you use in oil and gas for connecting drill strings, and we found that cold tubing is actually much more robust and lighter approach to deep drilling than more traditional oil and gas with drill pipes. So in terms of contamination, the first thing is obviously we need to clean before we ship, but we are developing a technology called SHIELD. It's funded by NASA, Planetary Protection Office, and it's an in-situ sterilization. And also en route sterilization. So when we fly to Mars, we're doing sterilization, and prior to drilling, we do in-situ sterilization. So the way to visualize it, imagine you have a cylinder around our drilling system, bottom hole assembly, that does UV sterilization, heat sterilization, and also we're using pneumatics and hydrogen peroxides to clean. So prior to going down, we have 4 ways of sterilization to get rid of contaminants. Right. Thank you.
Hello. I cannot hear anything, but I hope you can hear me. Yeah, great. Mm. Wait a minute. I'm trying to share my screen in the presenter mode, but I can see that it's fine, or yeah, it's okay. But I think that you can see not the right. It's supposed to be like that because you can see the slides did not change. Yeah, because now I'm changing the slides and I can see that it's not happening over here. So maybe the wrong window, yeah. Sorry. Is it fine right now? Yeah. Thank you. I'm sorry. Yeah. Okay. I hope the slides change. Okay, sorry for this short delay. So I would like to talk a little bit about something quite different than my previous presenter. So first of all, I would like to present a kind of an overview of the research of my team concerning, among others, the study of Mars terraformation process and the construction of a simulation system and mathematical model in this regard. So at the start, I wanted to define maybe the main objectives that are carried out during the research discussed today. So these goals form the basis actually of our scientific collaboration in our interdisciplinary team, which I will introduce in a moment. So these goals include, among others, the development of a simulation system to model the Mars terraformation process and the use of spatial big data processing using the developed algorithms for spatial information analysis. So today, actually, my main focus will be precisely on spatial data, which is actually our main area of exploration and a quite new approach in terms of Mars modeling, but I will tell a little bit more about it soon. So to start up, also I would like to introduce the leader of our scientific team, who is the Professor Christopher McCain of NASA Ames Research Center, who is of course a world-famous planetary scientist studying the terraformation of Mars, among others. And also I would like to emphasize that this quite long-term cooperation, because we are cooperating quite intensively from almost 4 years. It was actually because of the Mars Society. So this is the Mars Society actually we could establish our cooperation due to the Mars Society and the right connections. So our team during the time expanded a little bit. So first of all, I would like to introduce 3 people from Poland for Warsaw University of Technology. So we basically represent 2 faculties, Faculty of Geodesy and Cartography and the Faculty of Electronics and Information Technology. Of course, as I said before, the cooperation with, in particular, NASA Ames Research Center, Space Science Division, and also with Melinda Kares, so the lead of Mars Climate Modeling Center. During the whole time, our cooperation has been also expanded to include the cooperation with San Jose State University. In particular, an expert in meteorology and climate science, Alison Bridger, and cooperation with the university in Basel with Professor Christian Körner, who is one of the world's most renowned scientists in the field of alpine plain ecology, who actually helped us determine the conditions that must exist on Mars to appear on Mars. And a little bit about our simulation system. So we developed an energy model to simulate both the present day atmosphere of Mars and the changes caused by introduction of, for example, greenhouse gases and increasing the CO2 concentrations. We, of course, made a lot of data analysis. So we analyzed basically a combination of factors that make it possible to solve 2 key problems with Mars terraforming. So first of all is temperature increase of 60 K and the pressure increase of 100 times. Our planetary engineering included basically analysis of climate changes, but also changes in the composition of density of the atmosphere and temperature. And it was actually carried out on a planet-wide scale. To perform all the simulations and develop these algorithms, we use our calculation infrastructure of our university. This is the Center for Scientific Geospatial Analysis and Satellite Computations. As probably all of us here know, there are many, at least 13 different concepts on how to achieve the terraformation of Mars, and some of them are, of course, extremely expensive, and some of them would require the creation of completely new technologies that are impossible to develop today. So we decided in our research to consider only two relatively, yes, I emphasize relatively simple concepts. So a factory for greenhouse gases, which would gradually be released into the atmosphere. And the second one is an asteroid impact from the interplanetary space with high methane content and its control impact on the planet's surface. So this actually means single release of a large amount of gas at selected point. For our research and our model, we use MOLA, so Mars Orbiter Laser Altimeter data. So this actually data we use, of course, to project the elevation of each polygon on Mars surface, and we use this data with a spatial resolution of around 500 meters. Another important information is that we installed also, we use Mars Climate Database, so we installed the full version of MCD 5.3 version and performed calculations for any defined time and location in space. In terms of a calculation tool, so our computational approach is basically based on the discretization of both time and space. And the spatial model is actually based on the idea of a cellular automaton, as you can see here, with hexagonal cells of parameterizable size. So in terms of implementation, we use Gamma tools. So if you're not familiar with that, so this is a modeling and simulation platform that supports the design of specialized multi-paradigms and multi-scale models, different models. So they're basically a combination of the 3D visualization, GIS management data, and actually a multi-level modeling, let's say like that. What is new in our approach is that the spatial model of Mars is a kind of a grid of irregular shapes forming the Goldberg polyhedra, and they cover the whole area of the Martian surface. So here you can basically see how Goldberg polyhedra are formed. So the number of hexagons is increasing, depending, of course, on the accuracy of the projections we want to achieve, while the number of the pentagons is constant and is also always equal to 12. And this approach was proposed in 1937 by Michael Goldberg. And as I said, it creates a grid of hexagons and pentagons on a sphere or ellipsoid. And here is the projection of our idea. So as you can see, our baseline model of Mars is a polyhedron, which is composed of 4,002 hexagonal cells. And as the approximation of the Martian surface with 12 pentagons, and in total, yes, and 12 pentagons and 3,990 hexagons. So this quite unique meshing, which as far as we know to date has not been used in any Martian model, this produces kind of a homogeneous spatial resolution for the entire planet. And this approach basically avoids the problem of singularities or grid disorientation at the poles. So actually, this is also very often numbered as a common issue using traditional GCM grids. So here we can see the Mars topography with indication of 12 pentagon centuries, and also Viking landing sites marked in red. So the elevation of each polygon is determined from MOLA, yes, as I said before. Here also you can see the subset of these 4,002 cells in the model that include the Viking 1 site. So each cell has an area of about 36,000 square kilometers and a length scale of 119 kilometers. And here you can see the grid of 4,002 hexagons and the pentagons, and with marked identifiers, the selected part of it. As I said before, we have developed an energy balance model for Mars. I don't want to go too much into detail of that model. So here you can see basically the diagram that shows the subsequent steps of the iterative calculation algorithm. And you can see that for every hexagon cell, the energy balance of the surface was calculated considering many different factors, such as sunlight, advection of heat to and from adjacent cells. So also this this information here is extremely important in our model. So large-scale transport of a heat by general calculation, and Higgs exchange with the subsurface, latent heat exchange due to CO2 phase changes, and infrared radiation and greenhouse warming. So this model is in the terms of computing very efficient, and also provides results that are consistent with models that are more complex. Our model, of course, needs validation, and we validated the model by comparing the results to the Viking lander temperature and pressure data, and also Mars GCMs, MCD, and the NASA model. And it turns out that actually our model had a quite good, very good results. What also I would like to emphasize is that most visualizations of Mars use Robinson mapping, and we opted for the MOLVAD, as you can see here. And now I would like to go from the calculations to the actual results. So let's see what happens if we decide to build a greenhouse gas factory at the point marked with the red dot, first of all, in the Hellas crater, or hit this place with a methane-rich asteroid. So here you can see one of our results. So 100 gigaton asteroid over 100 simulation years, Martian years, so sols. So here, please note that despite the fact that the total mass of the greenhouse gases is the same, the process of the one-time release or stow loops steady production leads to different spatial effects over a 100 Martian year horizon. Here you can see another example. So a different scenario. So 1.5 megaton factory over 100 simulation years. Here we can see the habitable area, minus 25 Celsius degrees, and biosphere 0 Celsius degrees. And average temperature rise on Mars over 100 simulation years after the initial events. So here the obtained results indicate that when using the numerical parameters that are appropriate for ammonia in the simulation process, the average temperature increase on Mars exceeds 60 K. Regardless of whether the ammonia release was one-off or successive. So, however, the temperature rise graph analysis proved interesting that while the temperature rises more slowly in the factory alternative than in that one of the asteroid impact, the increase was monotonic in both cases. Another interesting graph is the percentage of Mars area with an average temperature above minus 25 Celsius degrees. So as I said before, the habitable area, and above 0 Celsius degrees, so the biosphere. And so here we can see how the situation changes around within the 100 Martian years, that means sols. And here we can see another example. So we can also carry out the analogous reasoning by deciding on a different quite better location of the greenhouse gas factory or asteroid impact site, so Tempe in the northern hemisphere, and also how the situation changed with the different scenarios with 1.5 megaton factory and 12 125 kiloton factories that are located in different places in the pentagons in our model. But basically, in this part, I wanted to show you what different simulations actually are possible with the use of our model. But now let's go back maybe to the main topic. So we decided, and we realized that the atmospheric conditions, we all know basically that the atmospheric conditions and existing on Mars today makes the existence of a life impossible. So we decided that for plant growth to be possible, the temperature should be several tens of degrees higher, while its diurnal fluctuation should be much lower. So for the growth of the first trees, the growing season should last at least 110 sols, Martian days, during which time the minimum temperature must not be lower than minus 6 Celsius degrees, and average temperature should be higher than 6 degrees, and maximum temperature must be lower than 40 Celsius degrees. So let's go to the results. Here you can see the first cells that occurred to be the ones that, and it was actually a little bit unexpected for us. So with the use of a high-resolution surface energy balance model for Mars, we computed the amount of a greenhouse warming required to warm Mars. And that is enough that trees can grow. So we found that 10 kilopascals of CO2 atmosphere. So this is actually a pressure level known to support plant growth. And the temperature suitable for trees to grow occur when the added artificial greenhouse thermal infrared gray opacity is around 0.01 optical depth. So this energy balance equation was applied to each cell, and in addition to the radiation terms, the surface energy balance includes the diffusive exchange of heat between cells. Also, the CO2 concentration and evaporation and the transport of heat by the atmospheric circulation. So we also tried to change parameters, but as you can see, when we change this artificial greenhouse thermal infrared gray opacity, the amount of the green cells, as we call it, so the cells, the places where it would be possible to for trees to grow, for the plants to grow, is larger. So these models actually do not illustrate the heat exchange between the atmosphere and the subsurface. If we add this parameter, it turns out that the tau should be around 0.27. But okay. 0.27. But what I wanted to emphasize in this model, so when we change different parameters, it turns out that still we found that the same area is the first area to be possible to plant the tree. So the low elevation of the Hellas Basin allows the concentrations of the first conditions that are favorable to tree growth. So that was actually something unexpected for us, because on Earth, the highest elevation tree lines are primarily in the tropics, but modulated by the location of the thermal equator. So it may be expected that equatorial regions of Mars would be the location of the first tree, but due to the Mars relatively large orbital eccentricity, 0.1, the southern hemisphere, which has summer near perihelion, has relatively warm summers. So in addition to orbital period of Mars that is 1.9 Earth years, so the long, warm southern summer provides the first growing season that is suitable, for example, for trees. And here is our projection of one of the designers. And to conclude, because the time is up, so our model and our methodology basically allows for conducting multivariate simulations of climate change on the lead planet, and the model is computationally efficient. So also our simulation system is based on open source tools, and it is made available in source of a code form. So here is the link for that. And the research also shows that it is possible to develop a system of numerical simulations that allows modeling the spatial and temporal variability of atmospheric parameters on Mars. Also, this model is actually fully parameterizable, so it's possible to indicate the different location, the volume of the greenhouse gas release, and so on. Okay, so thank you very much. If you have any questions, I will be more than happy to answer.
Can you hear me okay?
Oh, I can hear you now.
No questions here. Thank you so much for your presentation.
Thank you very much.
Hi, Dr. Verma. Good morning.
Morning. Morning.
I think we're all set for you to start. If you want to go ahead and share your slides, and then
Let me just try to share again. I think it's because it's Safari. I will just try this. Give me 1 minute.
March 2020. With a rich background in space robotics, autonomous robots, and robotic operations, Dr. Verma has significantly contributed to the Perseverance and Curiosity rover missions. Her expertise includes deploying robots in extreme environments and developing advanced systems for collision detection and autonomous science targeting. With over a decade of experience in Martian robotic operations,
Give me 1 minute. I might have to quit and come back in again.
Hello. PowerPoint notes view. We see your PowerPoint notes view now.
Okay, I will switch this to a PowerPoint view. Can you see that now?
Yeah, we can see your presentation. Yeah, there we go. That looks good.
Is that in the display view or the notes view?
It's in the display view. Yeah.
Great. Okay, so I will start from the beginning. Sorry about the delay. So I'm going to talk today about autonomous robotics and how we are using that for Perseverance progress on Mars. And so I'm just going to start with giving a little bit of a context of where Perseverance is right now. So far, it's continuing to explore Jezero Crater, and it's been an extremely successful mission. So we've collected 28 samples, and it's also created a depot on Mars where it's deposited 10 of the samples. And part of this is to hedge against the possibility that at any time when you're in a harsh environment, the rover can stop working, and you want to be able to make sure that we have samples to return to Earth. And the part that I'm going to focus on here is the reason it's been able to make so much progress is it's been very autonomous. Like a lot of what we're able to do now is largely autonomous driving. Almost 90% of the driving has been autonomous. And it's driven 29 kilometers since it landed on Mars, and it's broken a number of drive records. And what's neat about these drive records is it's not only has it sent the record for the longest drive on Mars. Before this, the record was set by Opportunity, and it was set all the way back in 2005. And it was one of these situations where you have to put together all of the resources and set up the drive optimally to be able to get that distance. But what we're getting now on Mars with rovers is just the consistency. So Perseverance has broken this record 23 times. So it's like consistently driving really long distance. And the longest drive, which was done over multiple sols, because we're sort of still limited by the amount of time available on any day to drive, is about 700 meters. And I'll also talk a little bit about how at the end of when you drive, because Mars is so far away and there are a lot of steps in the deep space communication to get the data back, we actually do some autonomous science so that you don't have to synchronize every end of drive with Earth. And then, Ingenuity had an extremely successful mission and logged 72 flights. It was supposed to have had 5 flights, and this is way beyond what was expected. So now we've also kind of really believe that, flight on Mars is a real possibility. So I'm going to go into this in a little bit more. Going into a little bit, as I was talking with Mars Society, it was a little bit of talking about like why robotics is so useful on Mars. So the Mars 2020 mission, you look at the back there, I think many of you have probably seen this picture before, it's the Jezero Crater. So in the crater, which I highlight in the white rectangle, is a delta, an ancient river delta. And what we have proven with previous missions is there was once flowing water on Mars. And so now, with this mission, the goal was, can we actually find signs of this ancient life? And what better place than an ancient river delta? And as you can see there, there's a channel where there was a delta in Jezero, and that was the destination. But landing, even though we're getting so good at landing on Mars, better and better, there's still an ellipse for landing. And Perseverance was like, almost an order of magnitude smaller than, say, Mir and previous missions used to be, but it still was like 8 kilometers. So you could be anywhere in that 8-kilometer black ellipse. And as you see, when Perseverance landed, it was trying to divert, because it has autonomous capability to divert from hazards when landing, on the other side of the delta. And the INSAT is a high-rise map taken from orbit, which shows in the white dots the locations that it was on where it landed and continued to explore. And one of the things that you can really do when you have a robot on Mars is do this science investigation at multiple locations. I mean, just as Earth is so diverse, Mars is incredibly diverse. And when we do science stopping at multiple hundreds of locations, you really start to characterize that location. And you're seeing on the right in the INSAT, Perseverance deploying its robotic arm, positioning instruments, and really being a scientist on Mars. And the mobility allows you to get to places, and with it, we can get measurements. And here, I'm showing the location of Perseverance. This is a little outdated from when I cleared these slides, but actually where it is now is, where you see in Neretva Vallis, under the L in Vallis is where Perseverance is right now. The other thing you can do when you have a robotic arm is, it has a 2.1 meter robotic arm and can position instruments really close to the surface. Some of these instruments are like incredible laboratories to do close-up measurements. So on the left, you're seeing Perseverance positioning the instrument, and there it has cut out a little, if you see in the white, a little circle, that is an abrasion patch. The surface of Mars is exposed to so much harsh environment. So the science and the interesting measurements are just a little bit beneath the surface. In fact, as deeper you go, the better. And you can see that it's cut away the surface, and on the right, it's position pixel instrument, and this is a measurement. And this is using AI on board, whereas it's taking measurements on board, the instrument sees what it studied, what's the mineralogy, and then it focuses on the areas where you can get better measurements. So it's automatically on board able to, based on the data, take more measurements in the most compelling science area. And the scale I show on the right there, if it's a really small font, but it's 2 millimeters. So we're really talking about taking very close-up measurements of Mars and being able to understand the history. And so here we are collecting subsurface samples. As I mentioned, we expect that if you're going to find signs of ancient life, they're below the surface. So it has a drill, and it can drill beneath the surface. And on the left there, you're seeing the drill positioned on a rock. And on the right is the samples. So as we are going, just the diversity of samples when you sample at multiple locations. So this is with Perseverance holding up the drill and looking with its mass camera at the cross-section of the target of the sample it collected. And because, we really want a baseline, some of these samples are what we call witness samples, where we take a measurement of the baseline of what we see on Mars, because, we may have measured on laboratories in Earth before we sent the rover, and we want to have a baseline from Mars. So there's atmospheric sample. And I don't have here the very latest sample, which is a Chayava Falls sample. This has been incredibly interesting to scientists, because it has made very compelling observations that it may actually contain signs of organic from distance past. So this really has everybody very excited about bringing these samples back. And there I'm showing a video of the process of drilling. The other part is Mars has a lot of interesting targets. However, there's also expanses of things that are more or less interesting relatively. So on board, it has this capability, and here I'm showing an image from Martian Sol 449 of the mission, where it has a wide-angle camera, the navigation camera, and you take a picture. The picture may look really benign. it has on board capability where it looks at 255 targets, up to 255, and says, in this, based on what the scientists told me in this area is interesting, what should I pick as the top 2 targets? And this is criteria scientists can specify and update. It picked 2 targets here. You're seeing those 2 targets, and then it shoots the laser at it and gets which creates a plasma and gets a high resolution telescopic image, which looks like this. So the rover is able to, at the end of a drive, without requiring Earth in the loop, say, I'm going to pick the most interesting target because I can't send all 255. I don't have the time to zap 255 targets, but I'm going to take the most interesting one and send the data back. And this is, you're seeing again 2 centimeters, and we couldn't cover that entire field of view with that, which was, tens of meters otherwise. And so we're doing a lot of this autonomous science, which is allowing us to do more science on Mars as well. I'm going to talk about how we've covered this big distance with autonomous navigation. So here is a summary of Martian autonomous navigation. And it's a little bit outdated because this was a paper we wrote, but it shows you all the different rovers that have had autonomous navigation ever on Mars. And the top row is where I'd focus your attention. So if you look at it, Perseverance has driven almost over 21 at this point, kilometers autonomously. This is considerably more than any other rover before it. And Curiosity is the most recent rover. So this is a huge leap. And this is what has really allowed us to be able to cover those distances, is this capability. If you look at Perseverance and Curiosity, they're very similar. So how were we able to make this big leap? So this is with very targeted improvements. So one of the biggest things that makes a difference is the computing. We've had to use radiation-hardened computers for missions that are, national assets on this scale, such large scales. We looked at the data because we've been on Mars for so long. So this is what's neat about Mars, is we've had rovers on Mars for so long, we have a lot of data we can mine. And we saw that we were railing the CPU, and even then 1/3 of the compute was being used for background processing, not even for the navigation. So we added a second computer, an FPGA-based compute capability, made improvements in the cameras, made the wheel design better, and then, of course, improve the algorithms, better ways to predict and do SLEP. It autonomously knows where Earth is, turns to Earth to establish communication. Because when you're autonomously driving, from Earth, we may tell it to go somewhere, but if there's a hazard, it knows to deviate. And so now it's facing in a different direction. So we had to do autonomous navigation and then autonomously find the sun, because that's the best way for it to find its attitude. So there were a lot of these capabilities that were very focused on us looking at the data from Mars missions and saying, where can we focus our attention to get the best improvement? And this is a video of actual driving on Mars. This is the actual images that the rover uses to do the autonomous navigation. And this is the drive that it did autonomously. So you're seeing what kind of terrain, freeform terrain, natural terrain it's navigating around, and the data that it's using. And on the right, you're seeing a video at the end of this drive. It did an autonomous turn for communication. We continue, the thing with Mars is we can continue to drive even further. And so we don't have GPS. There are not GPS satellites on Mars. So as it's driving, even though the rover is doing hazard detection, taking images, and it can avoid things right in front of it, it kind of slowly loses track of where it actually is on a map of Mars. So that's its true location, and it's drifting. And this is one of the reasons that we're limited to the maximum distances we have, because autonomous cars on Mars on Earth have the advantage of having GPS. So onboard localization, this is what we had the helicopter to fly Ingenuity. We actually needed a base station on the rover because Ingenuity used to talk only through the rover to Earth. And so it had this processor on the rover just for comms with Ingenuity. We now had this much faster commercial off-the-shelf processor, even though it was we were able to see if we could use it for other purposes. So right now, how we let the rover know where it is on Mars is it takes a panorama at the end of the drive, sends it to Earth, and humans on Earth register that panorama to the map of Mars. So you're seeing here at the base of the delta, we had this region. You can very clearly see it looks like a bacon strip. So it took a panorama and we told it, you're not actually here, you've shifted. And then we would on board reset the uncertainty and let the rover do it on Mars. This takes a whole solve. So at the end of a long drive, you need Earth in the loop for us to kind of do the GPS work from Earth. But now we are using the Snapdragon processor on board to actually take that panorama, send it off to that processor, and do the localization on board and tell the rover where it is. So this is something that we're in the process of deploying. We've demonstrated it a few times, but we had all that. Again, why would we be able to do this? Because we've been on Mars for so long. We had data from, years of driving that we were able to run the algorithms and make a very compelling case that it does, as well as humans. And the accuracy was on 100% of the cases. And it reaches, a 0.36 on average for 2.5 years of driving. With a lot of what I think goes to show here is because of our long history on Mars, we are able to make leaps in technology because of, and do it safely. And we are now in the process, we've tested it on Mars, we're in the process of deploying this capability, which will let the rover do even more science because we'll be able to collect the samples from farther apart diverse locations. So I'm just very quickly before I end going to touch on what is the future technology that we need for Mars robotics exploration. So there was a the study that was funded by NASA's PEST organization to look at, the NASA does a decadal survey every 10 years, and the last one was in 2023, which says, what are the priority missions? And so we did a study to say, what are the robotics technologies needed? And it's publicly available at this link. We were focusing on all the planetary robotics mission, but I will highlight here, because you're sort of focused on Mars, that a lot of this is very aligned with the Moon to Mars program, as you heard about earlier, and how we can enhance these. So I'm not going to go over all the 10 recommendations made in the study, but I'm just going to go over the 3 themes in the interest of time. So the one is that in general, to do planetary robotics for the missions, we want to go further and sample more. So we want to collect samples from very far locations and over long periods. So this is a mission, it's actually for the Moon, called the Endurance A. It's in the Planetary Decadal Survey. This mission is attempting to cover 2,000 kilometers in a couple of years. This is a lot more than we've ever done on Mars. So, if we can make these kinds of leaps on the Moon and on Mars, we can start to achieve these science goals. So this was one of the ways that we need to go further and we need to do more sampling, and it is going to require autonomous capabilities. The other one is, even though we're going to have a lot of capability to send heavier and heavier loads, science is about going farther and farther out in the solar system and going to more and more locations, even on Mars. And with smaller missions like the Discovery's missions, you want the rovers to be smaller because then you can send them on more missions. So I'm showing here examples. So you're seeing on the top picture, that's Curiosity. And then on the top left is MER. These are full-scale models. And on the bottom left is Sojourner. And on the right is emissions, the IRIS rover, which was as Eclipse payloads designed by university students. And you're seeing how much smaller we can get. And on the bottom is a demonstration, which was a demonstration, which is the size of Ingenuity helicopter with Ingenuity sort of flight, but added with wheels and actually a manipulator. Ingenuity weighed 1.8 kilograms. This sample recovery helicopter demonstration that was done, it weighs 2.6 kilograms. That's it. It has a 120-gram arm and a gripper. It can pick up 100-gram payloads. So we really are showing that we can scale down these robotics. So we can add it to any mission that is a potential lander mission. You can add a robot to do science and get to locations. And the last theme was to access extreme terrain and deep under the surface. Right in the middle, you're seeing the EELS robot. It was a test in the Athabasca Glacier. On the left is a concept to drill through Enceladus' ice, thermal probe. And then on the right, you heard from Chris as well, is we want to go further down, deeper on Mars as well. So these capabilities allow us to access. We want robotics to get to even more extreme terrain on Mars. Perseverance is getting to the rim of a crater, and Curiosity is going to a crater peak. These are extreme terrain. We are at the bottoms of these, but we're looking to get to more challenging terrain. So I'll just end with another one, which is aerial platforms. In the middle, you're seeing Dragonfly, which is a future mission to Titan. But Ingenuity has really unleashed the capability to say we can do aerial flight. And on the right is a Mars science helicopter concept. And on the left is a test of a Venus aerobot balloon. So with showing technology, some of the navigation and other capabilities port across different planetary bodies. So really, advances in robotics can enable planetary science goals. And the Moon to Mars initiative is really going to allow us to advance capabilities, particularly autonomous capabilities that allow us to do this even more. So that's it. And I would be happy to take any questions you may have.
Okay. Do we have any questions in the room? Can you hear me okay? Hear me okay? What were some of the toughest challenges you faced during development, and how were you able to overcome those challenges?
Yeah, so I think that's a great question. So one of the biggest challenge with planetary robotics really is you don't get to replace the hardware that you're sending to Mars. So often it takes a long time for the hardware to come together. And these are really complex missions. We have, a lot of instruments, a robotic arm and driving. So the toughest challenges was that you're seeing a full-scale rover here, but when you're developing, you don't actually have that hardware even in the Earth upper crust to test. So we had to come up with ways that you can test in that environment in simulation and other capabilities. You're testing autonomous capabilities. We have in the Mars Yard a Scarecrow rover that replicates, we take off the arm and it replicates the ground pressure of a rover on Mars for the full scale. And so we did a lot of testing that way. So I think that was some of the biggest challenges, is replicating Mars conditions and doing it before the whole thing has come together.
Computer on Perseverance, which is over 20 years old. What would be the benefits of having a radiation-resistant certified computer with more current cutting-edge capabilities for autonomous driving and the other functions that robotics would be performing on future missions?
Right. That ability to have a computer with higher computing is, I think, one of the biggest things that makes a difference with autonomous capabilities. Really, if you think about it, right, even on Earth, the capabilities we are seeing with AI and with self-driving cars and others is really in the compute performance. Like, yes, it's sensing as well, and other capabilities. That's going to let us drive further distances. Right now, still, when we get an image down on Earth, so we take a panorama at the end of the drive, human drivers navigate the rover and they decide, you saw autonomous capability, but we actually have a whole set of interactions between how much autonomy we give the rover, how much the human directs it. There's a scale of, the humans are still, when we have the information right in front of us, humans are still better than the rover. And I think we're going to get to the point where, like we do with, some of our airplanes, that it'll be able to do better than humans even when they have the same information as the rover. And right now, it's the compute limitation that doesn't let us do that. The other thing is that once we have that compute capability, you can start to make decisions on board and trade-off. No plan that we ever send to Mars goes exactly according to how we intended it to. There's so much variability. Mars is full of surprises. It'll be able to make decisions using the kind of judgment you can with experts on the ground. And I think those are some of the capabilities we'll see. So it's going to be extremely important.
Thank you for providing a wealth of data on the NASA websites. It's just wonderful to be able to go on there and go through those thousands of images and data points. It's been very helpful to us folks who are data miners. And that brings me to the question. How can you improve access to the public so that they can go through a sorted set of images and data points to mine according to their own interests?
Right. Actually, so one of the things I think is, so as you noted, right, every image that comes down goes directly to the public website. Like, in fact, all of them, like every image typically we take on Mars goes straight. And it's a great, even when we are going back and looking at some SOL, we have our internal database, but sometimes that can be a really good way to access that. There is so much information that come. And as a lot of you who are experts in data mining know, more than actually even the data, it is the labels and the context that is important. And that is one of our biggest challenge is the missions take so much focus of the team. And we are always trying to release the information. Actually, Ingenuity, when we landed, the images were not on the public website. And they worked very hard to say, how can we start to make those available as they come? So it's an ongoing process to do it. One of the best things we find is actually some are interns and students. So we had a student who was from a university and she was doing her thesis on data. So she came, and it's much, because we don't have the funding or the staffing to just spend on the data, but a student doing work will ask questions and say, oh, I need the camera models for this image. We can point them to it, and she was able to get it. And once she created that data set, we were able to determine what made sense with the data and release it. And then she was able to share it with her professors at her university and do her thesis. So, we are improving ways, but we're always interested in collaborations. When we have collaborations externally with some specific purpose, it allows us to take that specific data and make it available. Because I think just throwing out unlabeled data one of it is just where to put it and how to put it. But that is something I think we continue to look at.
Is this working? Yeah. I was wondering if NASA has published any studies that compare the cost and the benefits of sending a better lab to Mars versus the cost and benefits of bringing samples back from Mars and studying them on Earth.
Right, that's a great question. So, in some ways, I haven't personally done that because I'm more on the robotic side, but I will say Curiosity, the previous rover that I worked on, we sent the Kemen instrument, Kemen and SAM, the sample analysis on Mars. It was amazing. It's literally like a little laboratory we sent to Mars, packed on in the belly of the rover, and it would take a sample and drop it into Kemen and SAM, and they would do analysis on board. With Perseverance, I think what is interesting is it's a trade-off. You can send the laboratories, but these missions, by the Curiosity, it landed on Mars over more than a decade ago. Our science continues to improve, and what we are seeing, like the rocks astronauts brought back from the moon, they can find new things with new instruments now, today, that could not have been possible. So I think we should do both, in my opinion, where I'm not a particular expert in this, but I think there are advantages to both, because you're right, when you do them in situ, you can use that information to feed forward in it. But at the same time, if you bring them to Earth, the samples that Perseverance is collecting for potentially bringing back, when I look at what is going to happen and how we're going to study them in laboratories, it's kind of wild. I think it's literally the next generation, people who are still in school, who may be studying them and finding things in them all across the world that we wouldn't, we don't even know about, like techniques we don't know about. So I think there is an advantage in that as well.
Thank you so much, Dr. Verma. This was wonderful. It's always good to see you.
Thanks for having me. Thanks everyone for the great questions. Bye-bye.
Thank you. All right, we have a break in the schedule now. So we're going to take a 10-minute break. We're going to get the next speaker on and get all of our audio issues figured out. Thank you. Hey, Chris, can you hear me?
I can hear you just fine. Can you hear me?
Can hear you. Yes, we can hear you. We are going to troubleshoot the audio in our room though a little bit, but you can go ahead and bring your slides up. We'll introduce you in about 10 minutes. We're going to take a 10-minute break for the audience, but we're going to continue working on the audio system as well in that time. But if you want to bring your slides up and just see how that's looking, we can do that too at the same.
All right, let's give it a shot right now. I'll be pulling them up. Just give me 1 second. All right, how does that look?
Yeah, your slides look great.
Okay. Hopefully everybody feels the same way after the presentation.
I'm sure they will.
Mhm.
Hey, Chris, I think we're ready to go. We're going to go ahead and introduce you, and then you can take it away.
Fantastic.
You. All right, everybody. Strap in. We got a couple more speeches for this afternoon, this morning. Next up, we have Christopher Jeanette, who is an accomplished Air Force veteran, system engineer, and visionary leader in the space industry. Currently serving as president and CEO of Blackstar Orbital. He's a SpaceX alum. He played key roles in the Pad 40 rebuild, the Falcon Heavy Demo 1, and the Starship Thermal Protection Team. Most recently, he was lead hypergolic operations and system engineer at NASA's Kennedy Space Center, where he contributed to missions including SpaceX Dragon, Artemis 1, and several DoD launches. Everybody welcome Christopher.
Thank you very much. It's a distinct honor to be presenting at the Mars Society convention. Next year, I'd like to do it in person. Unfortunately, there's a couple of DoD things which we'll be speaking about today that our company is involved with. Blackstar Orbital exists to provide a next generation vehicle for both the commercial, government, and space exploration customer. How's my audio sound? Everybody hear me all right? All right, very good. Well, thank you for that introduction. I'm Christopher Jeanette, President and CEO of Blackstar Orbital. My co-founder and CTO, Kit Carson, who is an instrumental part of this team, and I have presented and put together several key slides specifically for this event, demonstrating how the Blackstar space drone can enable robust space exploration and development. Other members of our team involve Sean Hollis, former Artemis, Elizabeth Christensen, a key member of the Arizona Spaceport Alliance. She's our VP. We have some great advisors, astronaut Colonel retired Terry Virts, former ISS commander, worked on the Soyuz. He's been instrumental to helping us develop these next generation spacecraft. Whereas we like to think of our vehicle as a space drone, it's essentially based off the shuttle heritage. We also have Don Platt, PhD, our technical advisor. He's a professor at Florida Tech and CEO of Micro Aerospace Solutions. We have a number of PhD astrophysicists, orbital warfare experts, certified ethical hackers, space economists. Can't forget George Pullen, PhD, as well as James Wolfe and Nicholas Carlo. But let's get right into it. At Blackstar Orbital, we are redefining what a satellite can do by redefining what a satellite is. How are we doing that? We're developing reusable satellites, which launch like a traditional spacecraft and return home like a spaceplane. In other words, we're building easy to maintain, mass manufactured hypersonic space drones. Because there's a problem. Single-use satellites have many limiting factors. Every launch is debris generating, producing a number of ballistic threats. They are limited by their lifespan, typically due to solar panels failing or propellant tanks running out. That can include main propulsion for station keeping or RCS. These expensive $20 to $200 million satellites are often wasted well before their shelf life truly expires. They're not reusable at all. Single vehicle cost, single mission capable, and up to 20% of satellites are dead on arrival. This means that minor hardware failures can ruin expensive missions. We've all talked about, I'm sure there's been plenty of side conversations about valves during this conference. Manufacturing time, 18 to 24 months to manufacture and no refurb. We're overcoming these limiting factors. Blackstar is non-debris generating. We can collect and mitigate debris risk, as we'll show you in a little bit. They can be refueled and do refueling on orbit. They have a 35-year lifespan, much like the shuttle, and could relaunch multiple times. One vehicle cost, multi-mission utility. Technology failure. If there is an anomaly, we can return it home to refurbish it and fly it again. And we're looking to get it down from 3 to 4 months refurb at the beginning. We're looking to do it within 24 to 48 hours and do the scale of our vehicle that is absolutely capable. As noted, I'm an Air Force veteran. I started my career as an aircraft maintainer back in 2006, so many years ago. And the number of sorties that we can generate is an untapped advantage of the aerospace industry. We need to translate that to the satellite world. As mentioned before, Blackstar produces zero space debris. But what is the Blackstar? It's a satellite. The Blackstar is at its core a satellite bus with the capability to support a number of different commercial applications through its modular design. It's a space plane. While it launches and operates like a satellite, it returns home like a shuttle. After re-entry and unpowered glide, it is retrieved and refurbished to fly again. And it's a UAV. The Predator and Global Hawk UAVs have proven themselves on the battlefield. Blackstar can be a next generation version of these systems where the situation requires it. We like to call it a space drone as opposed to a space plane or a shuttle. Why is that? Whereas your Dream Chasers and the X-37Bs are your sedans, and some of them, for example, Dream Chaser and of course the classic shuttle can take people. This is an unmanned system. It's an unmanned platform, and it's a heck of a lot smaller. Where you have the sedans, we're the Ferrari, we're the two-seat coupe. Here's the general ConOps showing the multimodal nature of our vehicle. We can do everything from on-orbit servicing, proximity operations, ISR, assisted maneuvers, sustainment activities, fuel transportation services, and more. The way we accomplish this is through our Common Core space frame on a modular bus. What that means is we have a vehicle that is essentially a 36-gallon for the smaller scale fuel tank with the satellite hardware inside. We'll see a little bit more of that in a second, but just remember, it is a multimodal spacecraft on a Common Core airframe. That is the key factor that delineates Blackstar from other satellites. Here's a picture of our space drone. Not very large at all. Wet mass is going to be initially about 250 kilograms with a 40 kilogram nominal payload. We can bring it up to 60 kilograms for some of the hosted payloads that we're looking at. This can be everything from CubeSats that can be deployed to stored small sat hardware. We like to think that all the small sat operators out there, instead of focusing on building spacecraft, focus on what you do best, and that's developing the hardware that can be used to both their commercial advantage and our collective national security advantage. Because it's a hydrazine-based system, and don't worry, I am an SME in that field, it can take up to 1,800 meters per second delta V when deployed in orbit. We have some great footage of some static fires down the line. It's modular, reflight capable. Non-attribution is a major element of this. When it's up there, you don't know exactly what its function might be. They can have 25 Blackstars for commercial satellite use, but one of those might be a spy satellite. Tactical and commercial advantages, and this was built around the market signals, not the system itself looking for the market. What we mean is by that is, over the course of the last several years developing this program, we were polling both our friends and peers in the industry, as well as DoD, and trying to understand exactly where the shortcomings were in traditional satellite design and what we can do to mitigate and overcome it. There was a conversation that we had very early on with one of our key advisors, Colonel Terry Virts, where the question came up about hypersonics. And from there, the question then went to, what can you do with a pre-positioned hypersonic in orbit? And it turns out you can do quite a bit. As a dual-use technology, you can use it to either drop ordnance, or what I would like to think is we could replace many of the disposable satellite options that are currently out there, providing new opportunities for the customer. So here's 3 versions of our vehicle that we can talk about today. We have an ISR platform with synthetic aperture hosted payload, a modular spacecraft bus in the lower right corner, all the hardware is inside using a deployable solar panel to power it, and the LEO-C, the CubeSat and cargo deployer. That one's very interesting. If you have a CubeSat and you're on a ride share, you're more or less dependent on wherever that ride share goes. We can bring you to that last inclination change to get you exactly where you want to be. Also, the beautiful thing about that involves life science and material science research payloads. An important point of note, and you might hear me mention this later, is there are 14,000 runways around this planet that are longer than 5,000 feet. I think it makes a lot more sense to try landing at runways than trying to catch disposable or perishable items out in the middle of the desert or the open ocean. We love the concept of distributed networks. We see it as a critical factor in future satellite operations. That's enabled by things like edge compute, being able to process your data on orbit before you transmit it back down. For those of you who might understand, how the ground tracking systems work and how congested the data link budgets could be, that means a lot when you're using edge compute. If you're flying over these ground stations, you're only able to transmit every several hours, and it's a brief sweep in which you're able to do that. Why not pre-chew a lot of that data, maybe separate the signal from the noise, so you can more efficiently use your on-orbit operations? Blackstar is a multi-mission constellation enabling system. As mentioned earlier, because it's a common core space frame on a multimodal platform, you're able to do things like sensor and signal disruption, signals intelligence, hosted payloads. Again, the things that we had mentioned earlier. The profile is the same for the launch. Now, what you're seeing right there, typically our vehicle would launch maybe 2 at a time, 3 at a time. This is hypothetically if you were to stack them all in a Falcon 9. And because these vehicles are less than 2 meters long, or just approximately 2 meters long starting out, it is scalable. You can launch up to 92 at a time in a Falcon. Of course, that would involve a dedicated mission and a lot of other logistics. However, just to demonstrate the versatility of making this a constellation replacing or supplementation system. Why are we putting up constellations of satellites which may become a ballistic threat in the future? And there's also the environmental risks involved with dumping so much metal oxides into the upper atmosphere. Another thing we really enjoy is constellation resilience. We have some great partnerships we're formulating right now. Essentially, this allows you to either reposition a satellite to pull it down or to bring it back up. And that's critical. Again, if we're trying to be proper stewards in low Earth orbit, this is how you accomplish it. We can also do things like rendezvous and proximity operations, RPO. This could involve either intercept of a errant or a red team satellite, or what I like to think of is we can actually pre-position these as guard dog satellites, have them fixed to a larger, say a larger GeoBird, so if any interloper enters the keep out sphere, they can be investigated and possibly dealt with. So there's some key market verticals here. These numbers are always changing. In fact, I believe McKinsey just put out a report saying that the space industry will be about 1.5 trillion by 2035. Our economists are saying by the 2040s, it might be up to $4 trillion. So you have the defense industry. These can involve things like electronic warfare, ISR, orbital services, edge compute, orbital debris, in-space additive manufacturing, ISAM, and of course, transportation. Data services, everything from EO to climate monitoring, AI and machine learning, which could aid in the processing of data to supplement things like orbital cloud. Communications, everything from broadband internet access, mobile networks. I am in love with the idea that you can have a cell phone API that can communicate with the satellites. That is going to be revolutionary moving forward. It's that whole concept of democratic access to space. Let's turn it from a buzzword into a reality. R&D and sciences. This is a critical one as well. Scientific research, including astrophysics, planetary science, and earth science. Just some more key market verticals here, breaking it down as to how we achieve that. But there's one market vertical missing here, and that's space exploration and development, the final vertical, where it has a potential value that is unlimited. So without further ado, let's get into the stuff that we really want to talk about, space exploration and Mars. So deep space demos with the Blackstar. Science objectives, let's start there. Everything from cislunar orbital environment particulate characterization, deep space communications, network integration demonstration missions. We've been in talks with a company called Space Initiatives through our colleague James Wolf for deployable nanosat penetrators. That might be very interesting when we're trying to characterize things like asteroids or trying to find the right place to do deeper scientific exploration on Mars. Mini moon and moonlit prospectors and characterization demonstrations can follow. Let's talk a little bit about a asteroid lunar sample return concept that we've been working on with our colleague James. How? Since our vehicle features a hypersonic active glider deceleration technology, i.e. spaceplane with last mile capabilities, proprietary partner licensed avionics and subsystems, etc., we're able to send these out to asteroids with a prospector vehicle, fill up the Blackstar with the materials or the payloads, and bring it back to Earth. That's essentially what we're talking about here. Our vehicle is small, it's nimble, it's mass producible. We are predicting that once we get to economies of scale, we can build these for about $16 million. Direct sample return. This is very conceptual, by the way. The idea that you can land these Blackstars on a lunar lander, fill them up, and then do their lightweight and onboard fuel capabilities, bring them back up to orbit to then dock with the transfer vehicle and bring it back to Earth. I think it looks kind of cute myself. Solar powered for the wheels. Basically just taking a Blackstar on its own autonomous launch platform. Let's talk a little bit about our partner, James Wolf. This is the High Frontier preliminary mission architecture that was proposed. Essentially a deep space asteroid prospecting mission for small crews. This one will be called Call Sign High Frontier 1. The spacecraft would loiter in a transient lunar orbit, intercepting neo-moonlets, spent stages, and private salvage and claim operations to support deep space NASA Lunar Gateway operations, rapid response capabilities and investigation of phenomena, and frontline asteroid defense response. These missions would be about a month and a half. They would stay within cislunar space, and they would essentially be a neo-interceptor, which makes a lot of sense, I think, especially since we got Apophis coming in 2029. We should be turning these risks into opportunities, these threats into opportunities. It's a great picture of the High Frontier 1 catching a black star resupply, so we can extend those operations longer than a month and a half. Just some pricing on what it looks like. Obviously, economies of scale, the more you do these missions, the more they go down. These pricing figures are based on estimates and will become exponentially lower as cislunar traffic increases. Early deliverables will likely go to government and academic customers, with commercial customers to follow in the second half of the decade. By 2029, hypothetically, these fleet of tugs will operate between lunar orbit and the Lagrange points, driving a price parity between these points, which means that these numbers will start to even out as more people are up there and we start really getting to the economies of scale to pull down our Delta V budgets and sustainment budgets. Global market for asteroid mining industry is going to be quite significant in the future. These numbers are always changing. What we can do, commercial enterprise, why not bring these back and make a jewelry line out of it? Sounds funny, but what do you give the person that has everything? You give them their space, and this is how you do it. So this would be a premium luxury limited edition jewelry line, incorporating returned material samples into limited editions. So Black Star Deep Space return operations. Now we're going a little further out. Let's exit cislunar space and start talking about how we can do some atmospheric probes. So this would be a transfer vehicle as designed by our CTO and chief designer, Kit Carson. Really phenomenal and efficient design. One thing I did not mention is that Kit Carson is the former product manager for Amazon Kuiper. This shows a Black Star re-entering the Venus atmosphere. I'll show you the next one on that in a second, but the Atmospheric Explorer. The objective would be to study the dense and complex atmosphere of Venus with durable high entry descent system, high pressure resistant modules, atmospheric sampling, modular payload design, energy efficiency, and the benefits being comprehensive atmospheric data. We're told there might be life in Venus's atmosphere. Would love to get that answer sooner than later. We can accomplish it through these vehicles that re-enter the atmosphere and essentially deploy balloons. So I don't know how well you can see this on your screen in the audience, but these are essentially black stars where you have a large weather balloon that's inflated out the back using high pressure helium. One thing that may have been mentioned, and many of you probably know, is about 50 kilometers up in Venus's atmosphere, you're dealing with about 1 bar of pressure and similar temperatures to what you would experience on Earth, maybe a bit hotter. However, a lot nicer up there than on the surface, enough that you can have these structures inflated with a breathable atmosphere. And one bit of research that we've been doing for quite some time is the idea that you can take the Venus CO2 atmosphere, extract the carbon and the oxygen. You take the carbon, weave it into graphene, take the oxygen that becomes your breathing and lifting gas. There is nitrogen in Venus's atmosphere. So not only can you generate your own breathable air, but you can generate the envelopes in which you can maintain yourself in the air. And from there, if you can have an automated system, not too dissimilar from a von Neumann probe, eventually you can have these start to autonomously fill the atmosphere, cloud the atmosphere, if you will, with these carbonized vehicles. And from there, you can actually create a second surface in the atmosphere, thereby cooling the planet below. And you have something that might, in a couple of 100 years, be terraformable. Of course, let's not forget this is the Mars Society convention, and we're looking at a Mars terraforming, which we'll get to that in a bit. Not the terraforming part, but the Mars exploration part. So if it works for Venus, obviously you can do it on Jupiter. You just use a high gain antennas, using the modular sensor suites, powered descent, data storage relay. You'd have that on your vehicle that is parked in orbit. And what you essentially do is the same thing that we did for the Venus balloons, but you're doing it on Jupiter. That's a really interesting concept when it was presented to us, that not only can you deploy one of these, you can deploy multiples. So again, space exploration being the name of the game in spirit of discovery and knowledge, let's go and kick it into high gear, and let's do that with these mass producible space drones. The benefits of this would be new insights, providing data on the composition and structure of Jupiter's atmosphere at unprecedented depths. So you can actually sink this lower, you can have them at different altitudes. Long duration observations, extended operation time compared to traditional atmospheric probes. If we recall, the Galileo probe did a dive into Jupiter's atmosphere. Let's go a step further. Let's have a network of these, and let's set up a webcam. Let's get a live view of Jupiter's atmosphere. Let's have a look ourselves at what it actually looks like, and consequently, let's do that at the other gas giants as well. Enhanced scientific value, what it's all about. High data return to advanced communication storage systems. All right, now we're arriving at Mars. So we can take the same system and use it to do a series of different opportunities on Mars. So this is a black star during Mars EDL. So it's landing. Again, these vehicles are scalable. These are not the scale of launch vehicles. We do want to emphasize that. These are satellite class payloads. So before we show you the next page, let's talk about it. The Black Star Mars Hopper. Objective, explore Mars with enhanced mobility and extended mission life. Key features, a reusable landing system. Black Star's derived technology allows for soft landing and takeoff on Mars surfaces vertically. Powered CO2 extraction. As we know, Bob Zubrin helped repopularize the Sabatier process in his fantastic book, The Case for Mars, utilizing Mars atmospheric CO2 for methane fuel production via in-situ resource utilization. Multi-hop capability is then enabled. Again, it's all about that modularity. We can customize these payloads. We can have an unlimited number of different payload types. Let's not limit ourselves here. Applications, everything from geological surveys, ice cap exploration, resource prospecting, and atmospheric studies. Benefits of this being reduced mission costs, reusability and ISRU lower the need for Earth-launched supplies. Additionally, this can be used for resupply on point-to-point missions. So say you have your main Mars base, and you might have a network of, let's say, outposts further and further out. We can send these from the base and back as we're sending data back, materials back, and they're sending supplies to maintain that. This allows for greater area coverage. Multiple hops allow for exploration of diverse and distant regions. So it could look like something. It could look something like this, to where you have the Black Star stowed on a hopper vehicle, and you can have something not dissimilar from the Canadarm, allowing you to pull things out of the payload bay and bring them back in case it's a little out of reach for the astronauts. Again, this would be looking at about a 7-meter tall structure. Again, this is very conceptual, very early phase. You will be seeing more variants of this. You're the first audience to witness this. So back to 2024 before we conclude. Copy of that. Perfect timing. So let's go back to 2024. We're funded. We are funded by CT Holdings Incorporated. That allowed us to leave our day jobs either at Amazon or at NASA Kennedy Space Center and do this full time. We're really honored to have the faith and confidence of our investors, and we're getting more. We're currently in our funding round for $12.5 million. Black Star is also awarded an SBIR. We are under government contract, which means we are, in a sense, revenue generating right now. We are awarded SBIR Phase 1. We've been selected for a directive Phase 2. We can't say what that is yet, but you'll be hearing more about that in the very near future. Commercialization potential. We have had a significant number of companies reach out to us, requesting their services. So total, without going into every company and what they're doing, it's about $92.5 million in signed LOIs. And those are signed documents from reputable companies such as Cal Morris, Orbit Fab, Orbit's Edge. There's also a couple of DoD customers that we can't talk about, and Space Boxes, which we'll talk about another time, 15% manifest filled. So traction, we have demand signal, SBIR awarded, pre-seed closed. Wind tunnel model, that's right. We've done wind tunnel models for our feasibility studies. You're looking at a 1/2 scale model right there, and a static fire. Let's see if I can, actually, let's give you the big one. First flight prototype, and finally, a full-size static fire. Blowing out your ears, turn it down. We're all space people here, so you get the idea. This was 15,000 foot-pounds, and it was done in the Mojave Desert, one of the largest single sticks ever purchased by a private supplier. We got all the data we needed. That is orbit ready. So in terms of the bespoke tactical applications, we got it in spades. We've signed on with Jim Cantrell's Phantom Space to do our initial launches no earlier than late 2025. And on a small class vehicle, we can launch 2 at a time. And we're going to close out with partnerships with the Arizona Commerce Authority. We're on $7.3 million capital investment in the form of tax credits, workforce development credits with the state of Arizona. They've been fantastic. Shout out to the Arizona Commerce Authority, Brett Meekum, and everybody there who's spinning up the Arizona Space Commission, in which you'll be hearing more about that in the future. They really are evolving to be a hub. This is the facility that we selected. It's going to be 41,000 square feet at the north apron of the Sierra Vista Municipal Airport. They're getting their FAA FAR Part 433 license to be a spaceport, one of the few ones in the country capable of reentries. This is a notional reentry corridor of what that could look like. They're performing a feasibility study, and if you'd like to learn more, please Google it or Google us. So as far as our last slide's concerned, Arizona's been very supportive of this. Even though I'm calling you from 15 minutes outside the Kennedy Space Center today at our offices in downtown Titusville, we're planning on spinning up the lion's share of our operations in southern Arizona. And as far as the press is concerned, as far as the space guy, I don't think I can get a better title than that. They're calling us the right stuff, so we're going to prove it to them. They're the place that we need to be to make this happen. We're opening up our facility by 2026. And if you'd like to learn more, by all means, please go to blackstarorbital.com or spacedrone.io. With that, thank you very much for your time today. Everybody have a safe rest of your conference, and on to Mars. Thank you.
Thank you very much, Chris. Very impressive presentation. I think we have time for one question, if you're still there.
Absolutely, yes. Yes.
Why Southern Arizona? Maybe elaborate a little bit more.
Oh, sure, absolutely. Well, without getting into buzzwords, I've had it described as the 3 Ps. You have the people, proximity, and potential. So let's break that down. The people, for those of you who know, Southern Arizona is a major aerospace and defense hub. You also have companies like Phantom Space, Paragon Space Development Corporation. It's a really nice place to be. They have Raytheon, etc. You have you have a lot of veterans out there as well. And as a veteran myself, we understand the value of bringing those people into your teams as well. So that's the people, proximity. We might have our own private reentry site, and we'd certainly enjoy it if we had some company there from the other space companies. And finally, potential. We see the high growth potential of Arizona as veritably unlimited. Places like California and Florida are amazing. However, they're also pretty saturated with companies and talent. So you have these emerging space markets such as Arizona, where there is an ability for us to develop even further and really ingrain ourselves in the space community there. And the final thing is HB 2354 was established by the Arizona State Senate, written by and assisted by Brett Meekum, who's a phenomenal person everybody needs to follow if you want to learn more, to develop the Arizona Space Commission. So really, that's the potential that we're seeing there in simple terms.
Yeah. Christopher, first of all, thank you so much for saying that you guys got a seed round and finally you're able to exit your jobs at anywhere you worked before to work on what you love. That means a lot to me to hear that. Quick question is this. How long did you work on this project before you got the seed round? How long did you have to struggle before you got to this wonderful point? Thank you.
That is a fantastic question. The initial conversations we had with this really started back in 2018. The prior company of this, United Frontiers, had ended up raising almost $2 million 6 weeks before COVID hit. So much as it goes when you're forging an alloy in the pressure and the fires of, say, the COVID economy, if you will, we were mostly in stealth for this particular project for a number of years. It started off as hypersonic and defensive application research, but being that we had the swords to plowshares mentality, We only really started publicly announcing what we were doing last year. So about half a decade went into this concept. So you might have seen Kit Carson or myself at a number of different conferences, meeting people, asking a lot of questions, and really understanding what it would take to really supplement many of the use cases traditionally held by the small sats. This is a scalable system. This isn't the silver bullet. You still need your large, exquisite systems. K2 Space is a perfect example of that. Large, exquisite satellites as enabled by systems like Starship. So after the COVID economy, that's where I really dug my heels back into doing SpaceX, and then I spent 3 years at NASA as their lead hypergol propellants engineer out of Prop South. And ultimately, by the time February of 2024 came around, we were then ready to exit and have enough finances and convince our spouses that this is a worthwhile endeavor. So that's another key factor: is if you're going to do this, make sure you have support networks. You have for your families.
Thank you very much.
Thank you.
Okay, let me get the next one queued up.
All right. And for the last of our plenary speakers, we have next up is Dr. Bence Matias. Oh, yeah, okay, I was close on that one. Who is the founder and CEO of Genesis SFL, Hungary's leading space transportation service and LEO research provider. With a PhD in environmental engineering focused on soil microbiology, he drives innovation in space technology and agricultural research through products like GenoPlant portable labs and the MayaSat-1 biological incubator CubeSat. A blockchain developer and community builder, Dr. Matias gained widespread recognition for his Genesis 111 Mars terraforming mission, securing $2 million of investment on Shark Tank Hungary. That's pretty cool. His company partners with global organizations to offer affordable space research rideshare services, specializing in small payloads. Everybody welcome Dr. Matias.
to do that, we are also want to use different plants and woody plants as a host organism, because we want to use the growth of the root to regulate for continuously providing the microbes to the regolith. What is the reason? I'm a soil microbiologist, and I realized that most of the greenhouse gases production is happening in the agriculture, especially in under anaerobic conditions. I was comparing Japanese fields, paddy fields, compared to Hungarian lands, which are more ventilated, and we realized that the highest production of CO2, methane, and most of the nitrous oxides are happening underground. So it's a very good sign for us when we are talking about the Mars terraforming. So in this concept model, we are using 300 rocket capsules, which are planned to nurse the plants during the long 6 or 7 or 8 months travel. In meanwhile, the nose of this capsule is functioning also as a drill bit. I know that this hard impact, what you will see here, it's very hard to imagine, like mechanically, it's still challenging. We already conducted a couple of drop tests from Earth, from 2,500 kilometer altitude, and we were testing not only in wind tunnels, the flight of the capsules, but also on the impact. Only in one case, the drill bit survived the impact. So it's one of the most challenging part. But in order to we can transport anything like more complex living organisms in such a closed ecosystem from one planet to another, for sure we are going to need portable laboratories. And this is the point I feel it very important to highlight, that the reason is we cannot detect, or we couldn't really have any real conclusion about the organic detection on Mars, is the overthinking and the fear of the back contamination. So the Viking 1 and the Viking 2 landers, it's understable, because compared to the 60s technology, you know, they were also testing all of the parts from the rover for 5 years before they can actually put together. So it's a very old technology. We cannot blame on that. Even after that, that was a very big question in the scientific community after the second, the Viking 2. So they tried to replicate the same measurements on Earth, and they failed. So we cannot really use this data. But it's happened with the Curiosity. It's very interesting, because now the NASA and also the European Space Agency, in a joint collaboration, they build up the SEM laboratory. I don't know if you heard about it, but it's a very complex laboratory, including spectrophotometry, gas, and also liquid separation. But the main point is, because of the NASA high standard of the sterilization, we cannot use this data either, right? They are modern. The laboratory that they are using is state-of-the-art, but we cannot use it because until now we are still detecting the different reagents which are used for sterilizing the laboratory equipment. So because of that, even though we are detecting some sugars or whatever easy form of organics, we cannot really rely on them. So in this concept, we plan to transport plants as a host organism with a lot of microbes inside this capsule and penetrate the regolith. To do so, we carried out different tests in small scale environment, and we tried to mimic the topsoil of the Mars, but it's really hard. This, as you could see, the ice sheet of the Martian soil layers varies between the poles to the equator, and the reddish color which you see on the Mars, it's just the upper layer, and we all know it's a kind of result of oxidization, but it's not really that. Because of the high radiation, the minerals and the rocks are releasing chemicals, peroxides, and many things. So that's why all of this degradation is more accelerated. And but if you are going to the downer layer, and we know that because of the drill, the little holes that the preservants drilled, that the color of the soil is changing already upon a couple of centimeters under the surface. So the reason of the dimensions of the rocket capsule prototypes, it's because of the profile of the Martian soil, and including the ice sheet, which is like hiding underground. So we have to reach these layers if we want to keep the gas on the soil. Why it's important? It's important because of the molecular weight of the different gases. When we are talking about greenhouse gases production, we are basically referring three big categories, right? One is the carbon dioxide, which we all know because of the molecular weight is going to the downer layers. That's why the concentration is always higher in the downer layers on the soil than in the atmosphere, and is the same on the Mars. The other is the methane. The methane is like a very light gas, so it's going to escape when it has a chance. It's going always for the upper layer. And the same is true for the nitrous oxides as well. So we started to validate our concept in small scale prototypes and obviously in laboratory conditions. And we built up different soil sensors and different plant laboratories. It's very important to highlight they are laboratories and not a sensorial approach. And in a very small environment, I'm talking about half a liter oxytop bottles in a high number of repetition, we could mimic the topsoil of the Mars and regulate, and also the atmosphere. And we made two different runs. One, we are using the Earth-based atmosphere, and the other experiment series, we were using the Martian atmosphere pressure and gas composition. But we realized, upon 2 weeks, the microbes that we were applying, they were anaerobic microbes, also some viruses, but most of them bacillus strains. I will show you what we found out. So after the second week, we fill up the oxytop bottles by the injection of 1 microliter of mix of different microbes. And it's a very important number because we can use this to estimate how many rocket capsules we need to make a very thin atmosphere at least on the ground level for the Mars. So that's why that was important to us. Also, we were testing the flight test and the aerodynamics of these capsules before we started to build up the real size prototypes. And we learned many important things, for example, on the hard impact and things which we have to improve in the future. So these are our terraforming microbes candidates, what we can propose for Mars. And I disagree with most of the scientists who share that we need to modify genes for terraforming Mars. We don't have to, at least not on the lower eukaryotes level. Maybe in human DNA we can, think or consider some different alteration, but it's happening in the nature either way, okay? Especially in the lower organisms. In the case of microbes, in a couple of days or in a couple of weeks, we can talk about different generations of microbes already who are mutating, who are, they have some changes in the genomic level already. So here are our candidates for Mars terraforming who were living in a Martian environment for 2 weeks, and they not only survive, but they produce CO2 up to filling up half a liter of Martian reality. How many of these rocket capsules will need to create the first 15 centimeter thin layer of the Mars? And it's not that shocking. As you could see, according to our estimation, we are going to need 2,000 cubic meter of space to fill up exclusively with CO2. In this case, we can ensure this very thin but stable layer in the ground level. Why we are thinking about to releasing the gases on the soil poles, the reason is very easy, because we can capture them and accumulate the molecules for a longer time. And it's about one physical attribute of the soil, and this is the clay content. Higher the clay content in the soil and deeper you go, the isolation is greater. We could observe it in Mars, we could observe it on Earth. It's like a general pattern. So 2,000 cubic kilometer, I also expressed in your unit. I'm sorry, I cannot count in that just in kilometers. So you can imagine it as the half of the Grand Canyon. We have to fill up with the gases, okay? Or in dimensions like the Mount Everest, we have to fill up the mass, the volume of the Mount Everest with gases. And if we do that, we cover the entire Martian surface by 15 centimeters of CO2 molecules. And if we do it on the ground, we have a higher chance to capture this CO2, because what is happening on the Mars? There are 4 seasons changing, right? And in the winter, it can be so cold that the atmosphere is escaping for 2 different reasons. But one of the reasons is the atmosphere is freezing out. The CO2 is freezing out from the atmosphere. So when we see these big surfaces of ice on Mars, is just a smaller part is waterized, but the majority is CO2 ice. Okay, so that's why we know that there was obviously, and there gases which are being reproduced by, we don't know by what, maybe microbiological processes already, but maybe can be, just because of the minerals activity. So the main point is, according to our estimation, we need 40 years if we launch every 4th year a Starship with 300 rocket capsules in it. So we need only 1 spacecraft per mission. And so every 4th year, we are injecting 300 capsules. And for 1 capsule, we need only 1.2 liter of microbes, okay, to inject this area. One of the most difficult part for us was also funding the funding. So this is the funding of the first layer of the Martian atmosphere, let's say. We applied for the European Space Agency Business Incubation Program. And the first time we were rejected because the Mars terraforming concept was part of my tender, okay? So the ESA is basically following the NASA protocol. But my question is, we are so afraid of this back contamination. Roscosmos applied the same sterilization protocol like NASA. You know what I'm trying to say? The Chinese, India, using the same protocol. I don't think so. I think we already bring many microbes to Mars already. So, and vice versa. So this is the politics. I understand, but it's slow down many processes. So after half year, I tried again for apply for this 50 grand. It's 50K grant, and they said, please erase the Mars terraforming part, and your tender will be okay. And that was so. So we gained the tender, and we could finalize the development of the Genoplant laboratories, because we realized that nobody will finance these kind of long-term missions, at least not in our environment. We are coming from Slovenia and Hungary, in which we just joined to the European Space Agency in the recent years. So basically, we are getting funds from downstream space utilization, but not for upstream. And even if though upstream, we cannot mention the Mars terraforming topic because nobody will support us. But we knew that if we are finalizing our portable laboratories, we can use it also in our rocket capsules, because the plants will need the health monitoring during the long travel. I tell you what is the catchy point is the biomarker discovery, but our time is limited now, so I'm going to proceed. From a private laboratory, we gained 150K euro for biomarker discovery, because I knew that it will be a very interesting point, because the pharma companies are, sponsoring the ISS research because of the hope of the biomarker discovery. But it's a little bit different in the case of the plants, and I will understand, and I will explain you why. So because of from the public sector, we couldn't get enough funding. We had to open for the private sector. And we were a small company, so we couldn't release public shares immediately, but we modeled the shareholding system on a blockchain, and we deployed the Genesis 111 utility token, which, many people were smiling because, they were having the idea it will be the same like, Doge to the moon and things like this, but it's a serious token, because at the time when we are selling one of our laboratories, we are also distributing back the money for our early investors. So I wanted to say thank you for everybody who supported the blockchain activity. And within 3 months, it seems to be a good decision, because we reached a 2 million market capitalization on the blockchain. It's very nice and very, very, very nice numbers, but you should understand that we cannot use this money really. It's part of our marketing. We have 1,000 investors from all around the world who put together like 150K, and now we are growing big. But why we are doing it? Most probably we won't, plant trees, cut trees to print money on Mars. So we are not, most probably we are going to use a blockchain technology. This is part of my study, how a microeconomy reacts to different things, different facts, and it's very interesting to follow up. We also, on paper, we got 2 million from the Shark Tanks, from the before mentioned Shark Tanks, which until now we didn't receive. So they stated on the Forbes, they stated the sharks on almost the mainstream that they, in past tense, they invested in this Mars terraforming. But I can tell you, I checked my account in the morning and the money didn't arrive yet. So we were, taking care of our own community, and we started to pay back the investments to them already. In the first year, we paid back 30K already from the 150. Other big and strong pillar for that kind of research is the biomarker discovery. If you are interested also the scientific outcomes of our research, you can check one of the electrophoresis or the renewable and sustainable energy, but I can tell you in summary what is the main point. We discovered 3 different biomarkers to early detect nitrogen, phosphor, and microelements in tomato and in other crops before their visual symptoms appear. I repeat, before its visual symptom appear. What does it mean? When you see the leaf, it's getting yellowish, it's already late. When you detect from any sensors changing in the chlorophyll, it's already late. So we have to know what the signals of the stress for different biotic and abiotic factors on the plant if we want to, apply fertilization. And that's why we can sell these laboratories also among farmers, and that's how we are making money, and that's how we are sponsoring our own research, because from the biomarker discovery, it's not happening in like a human medicine case. You should know about the GlycoStore. It's a human database in which they store correlation of different glycanic structures to predict diabetes 2 and cancer. And it's a very smart thing, because if they discover a biomarker, the market price will be determined according to how many people have this sickness and how the government can save money on treating those people, right? But in the plant biology case, it's not that profitable. Who will give me any money because of my 3 biomarkers? I know the plant will have a nitrogen deficiency sooner than anybody else. But you know that nobody cares. Nobody really cares. Okay, so what was most important to us is push on the market the GenoPlant Analyzer. So the last year, October 2023, was a very big milestone in our company, because since then we have a boxed product. So from a research group, we transformed our team to a company, and we started to distribute these laboratories. It's a B2B approach. It's for businesses. It started at 28,000 euro per unit, but basically bigger farmers are using it, and it's still very cheap compared to the traditional methods like HPLC. What is the main difference? In the HPLC and traditional analytical tools, they are using pumps and many other sensitive assets to perform complex analysis. In this system, we are not using any moving part. So we are applying high voltage for separate the molecules and ions according to their charge and size in liquids in record time, under 2 minutes. So also, we made 2 million market capitalization on the blockchain, which means that we sold 10 laboratory devices, and we also had some pre-sale in the end. So what is happening now? We are turning out from the laboratory to low Earth orbit. This is the first time when we can examine microbes, plants, yeast, human DNA in an orbit than never before. And this provided us an excellent opportunity to continue this Mars terraforming research, because the plants and the microbes that we selected in the laboratory, now we have the chance to bring it up to Earth low orbit. And a couple of days ago, it became official. So our company, the Genesis, actually is having now the last slots for the exploration company mid-size demonstrator space flight. This is the Nix. I don't know if you heard about it. It's a European company. They are also supported by the European Space Agency. It's a German and French-based company. So there are many people who joined us already. For example, Mate Feit is a wind tunnel European and world champion, and he's going to send his DNA in our biological incubator CubeSat and we are going to examine the changes on the genomes. Before the flight, we are going to run a PCR. After the flight, we are going to run a PCR. And the thing is, we are not only interested in the differences of the degradation of the helix, but we are trying to attempt to observe the rebuilding processes, the bridges, and so on. So it's a very interesting thing in the modern medicine, because there are gene banks who are storing the sport people DNA and different genomes for a longer term, preparing for another COVID or another big catastrophe, because their body, their system is resistant. So this is our biological incubator. It's not a render. This is the actual concept. We are using two main boards, one inside and one for outside measurement. In one main board, we can connect 6 different sensors to measure, basic parameters, also in the space environment and also inside the CubeSat. It's connected to a programming chip, and on the left side, you can see a ground gateway. And this is the actual concept. We are programming it in Python. And for that demonstration purpose, we just keep a small plant inside the cabin. But actually, for our 2025 mission, we are bringing up 980 different biological samples, including human DNA, plant, yeast, lower eukaryotes, including algae. And the main point is, it's a 3-orbital space mission. So we are going to polar orbit, which is it's not common. And I think astronauts were not in polar orbit yet, not human DNA, and not any other biological samples. Correct me if I'm wrong, but I want to believe that this is the first one. These are our partner, the exploration company. This is the mid-size spacecraft, which called Mission Possible, and we joined to that spacecraft now. They have the first re-entry test this year, 1 month ago, and this is what's going to happen is 2025, between February and July, most likely. This is the 300-kilogram payload capacity cabin, and this is also a part of a test, because in 2027, the company is going to continue building up even a huger spacecraft to carrying up to 3 tonna to International Space Station and other space station on low Earth orbit. So I hope that there will be more students present here. So let me to I wanted to give 15 places to set up 3 different biological research for the Mars Society, and also for the students who are part of this work. So I would like to ask you later to, we can arrange it. In this CubeSat, we can fill up 5 different racks and hosting altogether 980 biological samples. A part of the DNA, we are going to also examine different plants, seeds, yeast, as well as root growing algae in a form of lyophilization version. So we are going to regrow the algae after the space travel. And the application deadline is 31st of August, the end of this month. So if you have students who are interested in sending a biological samples with us, this is the deadline, because after that, we are going to close the biological capsule and going to be prepared for a California launch between 2025, February and July. And after orbiting 3 times around an altitude of 800 kilometers, so it's almost the double height of the International Space Station, and we are also crossing charge zones 6 times in the poles, right? That's why because of the gravity of the Earth, there are many charged particles. That's why we can see the Nordic lights, right? So we are going to cross these zones 6 times, and it's provide us an excellent opportunity to measure the space effects on biological samples, and we can mimic the longer space travels in the term of the radiation doses and the other particles which we are going to cross. So thank you very much for your attention. It's a very good question, and I think we should have an answer from the JPL and an exact answer. But I heard about this study, they still cannot decide that forms of organics was produced by exclusively chemical processes or that was some biology behind. So if we can answer these questions and we can be sure after, I think we can be more brave when we are talking about, injecting especially. But when we are talking about manned missions to Mars, within a decade, when we are going to print and going to make constructions, obviously we are going to contaminate each other planets. So if we are doing it for real, and I want to apply like the same in the agriculture field, it's just a big, I consider it as a big field. So if we bio-inject in a correct way, we also can benefit. And for the human colonies, it will be at least the first layer of atmosphere, even if in a ground layer, because it's going to happen anyways. So I just trying to, save time.
Thank you very much. Thank you.
So we've reached the closing. And so last night, during my remarks at the banquet, I mentioned some of the initiatives that we're going to be doing during the coming year. We're of course, going to be continuing all of our existing initiatives, the operation of the Mars Desert Research Station, the Flashline Arctic Station, the rover contests, the education program involving engineering design contests for high school students. And then we're going to be launching a political initiative to have Congress demand that NASA present it with a plan to get humans to Mars in 10 years so that the discussion of the possibility of this can be opened. Okay. We're also going to be doing one more initiative that I failed to mention last night because there was so much going on and I didn't get to mention it, but I'll mention it now. Then this is a Mars Technology Institute initiative. What we're going to do, I mean, look, there's a number of key technologies needed to settle Mars. And one of them is in the area of food production. Mars is going to have much more limited acreage, if you will, than is possible for agriculture on Earth. And they'll have to either be doing their farming in greenhouses or in tunnels that are lit artificially, and either one of those is going to be terribly constraining. And while it's certainly possible to do human Mars expeditions without any new food technology, an expedition can just bring its food, and a small Mars base could be supported by a greenhouse. But if we're ever going to have cities on Mars, and I mean even small cities like 10,000 people, 30,000 people, we're going to need to have a new food production technology that can produce food at least an order of magnitude, if not 2 orders of magnitude, more efficiently from an energetic point of view than how it is done in conventional agriculture on Earth. Okay. Now, there's a variety of such processes that people have discussed, including using bacteria to transform methane into protein, and then either using that directly or feeding it, for instance, to fish in an aquaculture type setup, or using yeast to transform methanol into protein, which is in fact directly edible, or once again, feeding it to fish or livestock and creating a more attractive form of food. Okay, but we need to advance on these things. We need to have processes that can do it more productively than the current state of the art, that can produce more attractive forms of food, that can integrate it better with such things as aquaculture systems and so forth. So what we're going to be doing is we're holding a contest. It's an international contest, and there's going to be 3 divisions in this contest, okay? There's going to be an open section, which is open to anyone, including companies, okay? There's going to be a university section, okay, which is for university students or professors at either graduate or undergraduate level. And then there's going to be for students because frankly, there are high schools that have reasonably well-equipped laboratories that can do experiments of this kind. And we're going to want, you might call this a grand international science fair, if you wish. We want people to demonstrate processes that can contribute to this goal. And the thing about this is the following. Okay. Number one, this technology is needed to settle Mars. Number two, okay, the winners, okay, a condition of entering this is that they given the Mars Society an opportunity to patent the process that they invent. And if we do patent it, okay, they will get a quarter of what we get if we license the patent, or a quarter of the equity of the Mars Society's share of any spin-off company that is created around this technology. And of course, they'll have the name on their patent, okay? And of course, there'll be prize monies as well. So we intend to create companies that will commercialize this process and make money that will help fund further research by the Mars Technology Institute, okay? And then finally, you see, there is a slander that has been used historically against the space advocate community, is that we don't care about the conditions of poor people on Earth. We're just all up in space. Well, there's nothing, absolutely nothing that anyone could do that could do more to better the condition of the world's poor than develop technology that can produce high quality food cheaper. Okay? That is the most profound contribution you could make to the condition of the world's poor. And we're going to show that by addressing the problems of the human settlement of space, we're going to make a major contribution to that. Okay? So that's something we're going to be doing. There'll be more details on this coming out. The Mars Society will produce a press release. We'll probably produce a video that will be posted in which this is explained in greater detail. The contest rules will be stated, etc. The prize is listed, all that kind of thing. And we're going to be looking for corporate sponsors for this, so we can actually hopefully well, increase the value of the prizes. Because by having a student section for this prize, I believe we're going to be doing a major contribution to STEM education in the biotech area. And biotech is an extremely important area for advancing technology in the 21st century. It's a revolutionary area, and we're going to be helping to get young people to actually exercise their talent in it, and perhaps get some to make that their careers. So that's another thing we're going to be doing. Okay, so, and they'll probably be doing some more things beyond all that, who knows? Okay, but anyway, I think it's going to be an exciting year, and we look forward to seeing you all again next year. And by the way, with this contest, I should say, the finalists for this contest will face off at next year's convention. Okay, so you'll get to see the finalists present their stuff and see how it comes out. It should be quite exciting. So on to Mars.
And just a reminder, we already announced that next year we're in Seattle. Yeah.
Okay. Next year, we may be in Seattle. Okay, but this is, we need to examine our options. Seattle is definitely in the running, but we're also considering Los Angeles as well. We need to look at a number of options on that. But it could very well be here, but if not, LA is just a hop, skip, and a jump away. All right. Thanks.
Thanks, everyone. Have a safe trip home. See you next year. The conference is over. We don't have you on the schedule. Next year. Sure. Thank you. Likewise, Stephen. Yeah, for sure. Hey, how you doing? I'm glad you made it. Oh, thank you so much. Thank you. Yes. Hope to see you in Sydney next year. Yeah. Yeah, I don't know. No, we'll probably do September next year. Yeah. All right, guys. Have a safe trip home. Yes.
Want to let you know, I can put aside an hour and a half before I leave.
Oh, we got everything covered. We're just gonna put stuff in.
See you around, okay?
Yeah, man. Good to
Absolutely.
see you.
Thank you for everything.
Good to see you.
First,